Hank and to all the organizers for inviting me. That's really a great pleasure for me to be here. And so, as Toan said, I will try to give really some basic things about the mathematical theory of fluids. And so I will focus on the two most famous equations for fluids, which are the so-called Euler and Navier-Stokes equations. So let me give you first some brief outline. So first lecture will be some kind of introduction, some presentation of the equations. And I will also try to describe the main mathematical tools that you need for the analysis. So I will introduce the so-called Leray projector. You will see the vorticity fields, things like that. So after this introduction, this pretty long introduction, we will move to the question of existence of solutions for such equations. Okay, so we will discuss a little the theory of existence and uniqueness of solutions for this kind of PDEs, and we will first focus on smooth solutions. And then we will turn to irregular solutions, because of course in fluids, in nature, you can observe irregular structures, okay, and you want to be able to describe them, and the framework of smooth solutions is no longer adapted to them. Okay, so we will discuss the theory of irregular solutions. So it will be the core of the lectures, and if I have time, so there is a maybe here, there may be a fourth section, okay, which is devoted to the transition from Navier-Stokes to Euler. So as we will see, the Navier-Stokes equation is to describe viscous fluids. Okay? And in the Euler equation, you neglect viscosity. So there is a legitimate question, which is, when can you neglect viscosity? Okay? When can you replace Navier-Stokes by Euler? So there is a kind of asymptotic problem when you send the viscosity to 0, and this is a very delicate problem that maybe I will be able to discuss later. So that's the outline, and we'll start right now with this presentation of the equations. So first thing to say about Euler and Navier-Stokes is that they are macroscopic models. So macroscopic here is opposed to microscopic. That means we do not want to follow each single trajectory of each single fluid molecule. Okay? We want to have some kind of larger scale view, right? We want to see the fluid as a continuum. And this continuum will be described by a space variable x. And this space variable x will live in some domain omega of Rd. Okay? So D will be 2 or 3. Of course, we live in a 3D world, so D equals 3 is the usual thing. But sometimes you have flows that are invariant along one direction, and so you can restrict the plane. So D equals 2 will be the case of planar flows. Okay, so to have this vision of the fluid as a continuum, there is a key notion which is the notion of fluid particle. Fluid particle. So for each time t, and each position x, we will look at our fluid, and what we call fluid particle at time t at position x is some kind of elementary volume. Okay, so you have, so this fluid particle is some elementary volume v of t and x with some given typical length, lambda, and this typical length will be chosen so as to be much larger than the mean free path of the molecules in the fluid. And it will be much smaller than the typical scale of the flow that you want to study. So you have this kind of elementary volume, this fluid particle, and inside, as you have chosen this volume with a typical length which is much larger than the mean free path, you have, in average, a large number of molecules which are colliding. Okay? And through this collision, there is some kind of averaging process. Okay? So you will be able to have this continuous vision out of it. And of course, this volume should not be too large because you still want to be able to describe something interesting in the flow. Okay? So you should not average over too large distances. Okay? That's the idea. And so, in each fluid particle, you will be able to define some macroscopic quantities. Okay? So, for each fluid particle, you can make averages. You can define average or, let's say, macroscopic quantities. Let me give you two important ones. The first one is the so-called velocity field. So for each particle, that means for each t and x, we will be able to define some velocity field u of t and x, which will belong to RT. And this velocity field will be defined as an average of the velocities of the molecules inside the volume. Okay, so this will be 1 over the number of molecules inside my volume of the sum of all velocities. Okay, this is ui, that's the ES velocity, the velocity of the ES molecule. So that's a very important macroscopic quantity, the velocity field. And of course, you can also define some density field which will be 1 over the volume of my fluid particle times the sum of all masses of the molecules. So you see, this is the starting point. We want a continuous model. So in each point, we select some little volume and we can define, attached to this volume, some macroscopic quantities. And so the point will be to get some equations on these macroscopic quantities. Okay. The point will be to describe the movement of these elementary volumes. Okay. So of course, I will denote by x of t and y the position at time t of the fluid particle that was initially in y. And the starting point is to say that my fluid particle will be evolving following its velocity field. Okay, so we have a basic dynamical system. The time derivative of x will be u of t, x of t, and y. Okay? And initially, I said the fluid particle was in y.